Alright, final two gas laws that we're going to learn about. They're Dalton's law of partial pressure. That's this first one we're going to do. We're shortening that to DLPP for short. I don't feel like writing or saying Dalton's law of partial pressures. The final one is the ideal gas law. Ideal gas law. That one's a little more complicated. There's a bunch of variables in it. 1, 2, 3, 4, and 5. But luckily, I will give you 4 out of the 5, so it's just like solving any other equation. But let's go back to Dalton's law of partial pressures first. Dalton's law of partial pressures says that the total pressure of a system of gases is equal to the pressure of the individual gases. So if you think about it like a circle, you have your entire circle, and it has a certain area. Now you can cut that circle into as many pieces as you want, but that area of the circle doesn't change. The area of all these little pieces, if you add them all up, you still get the area of the total. Now, instead of area and little pieces, we're going to do the same thing with gases. So, if we look at this first problem, a container of gases contains 1.5 atmospheres of carbon dioxide, 0.5 atmospheres of nitrogen monoxide, 0.4 atmospheres of fluorine gas, and 5.2 atmospheres of helium. What is the total pressure of the gas mixture in this container? So the question is asking, what is the total pressure? So really, we want to know what the pressure of all the gases together are. Well, our first gas, our first little piece of the circle, is 1.5 atmospheres. Our second piece, 0.5 atmospheres. Our third gas, 0.4 atmospheres. And then our final gas, 5.2 atmospheres of helium. Now, these are the pressures of the individual gases. We want the total pressure. So we're going to take these pressures and we're going to add them. So we're going to take the pressures of all of our individuals and add them up to find the pressure of our total. So 1.5 plus 0.5 plus 0.4 plus 5.2. So our total pressure is equal to 7.6. Oh wait, no naked numbers. Our unit is atmospheres. 7.6 is just a number. 7.6 atmospheres is a pressure. Dalton's law of partial pressure is pretty easy. Let's do number 2 together. What is the pressure of a mixture of nitrogen gas, N2, and oxygen gas, O2, if the partial pressure of nitrogen is 594 millimeters mercury and the partial pressure of oxygen is 165 millimeters mercury? So this part, we have two gases. We have N2 and O2. If we want to know the total pressure, what is the pressure of a mixture? That's the same thing as saying what's the total pressure. We're going to take the two parts. Nitrogen is 594 millimeters mercury, and oxygen is 165 millimeters mercury. So we're going to take the two parts and add them up. Find the total. That will be the total pressure. That gives us 759 millimeters of mercury. Now, a little common sense thing. If you're solving for a total pressure, it needs to be higher than any of your individual numbers. So 759 right here is higher than 165 and higher than 594. It's a pretty reasonable answer. Going back to the first problem, our total was 7.6 atm. It's the total pressure, so it needs to be the biggest number. If it's all the pieces of the circle added together, the circle obviously needs to be the biggest one. So we're comparing that to 5.2. 7.6 is bigger. 0.4, 7.6 is bigger. 0.5, 1.5. In all cases, 7.6 is bigger. Now, number 3 is going to twist this around a little bit. This time it's asking what is the partial pressure of hydrogen gas in a mixture of hydrogen and helium if the total pressure is 600 millimeters mercury and the partial pressure of helium is 439 millimeters mercury. Now this one, we flipped it. I gave you the total pressure. And I'm asking, what is the partial pressure of hydrogen? So again, if we go back and think of it like a circle, we only have 2 gases in this. So let's just divide it in 2. We know that one of these is hydrogen, the other one is helium. Now, I drew my circle perfectly in 2. That's not necessarily true. This is just as a model. We know that the entire circle is 600 millimeters mercury. And we know that the helium part is 439 millimeters mercury. Hydrogen is unknown. Hydrogen plus helium equals total. We know the total is 600. We know helium is 439. When we don't know it, we call it X. Does this look like an algebra formula that you can solve? I believe so. So we're going to take 600, subtract 439. Anything in this mixture that is not helium has to be hydrogen. So we get 161 millimeters mercury. 161 millimeters mercury. Now, the first 2 problems, the biggest number was the total pressure. In this case, we solved for a partial pressure, so it should not be the biggest number. The total pressure is 600, so our answer should be less than 600. 161 is less than 600. That's a pretty reasonable answer. Now, for the 4th one, I want you guys, you're going to pause the video and try to solve this. Just take your time. You're just doing the same thing we've done above. This time you just have a few extra numbers. You can do it. Pause the video now. In a few seconds, we'll move ahead to ideal gas law. Okay. Welcome back. Obviously, you got the right answer. Duh. So, now we have some ideal gas law. Your ideal gas law, I wrote the formula here. I'm going to rewrite it for you. It's PV equals nRT. Or, to use the words, P, pressure, V, volume, N is moles. Why don't we use M for moles? We use that for meters. R is the ideal gas constant, and T is temperature. So to re-say this formula in words, it's pressure times volume equals number of moles times your ideal gas constant times temperature. Now, in all the other gas laws, we used Kelvin for temperature. That does not change here. Anytime we have temperatures, we need to make sure they're in Kelvin. So one more time, there's your formula. It's also written over here. Let's do some practice. If I have 4 moles of a gas at a pressure of 5.6 atmospheres and a volume of 12 liters, what is the temperature? Now, ideal gas law has 5 variables, so we're going to write 5 things. P, V, N, R, T. If I have 4 moles, the variable that is moles is N. So 4 moles. At a pressure of 5.6 atmospheres, there's pressure, 5.6 atmospheres, and a volume of 12 liters. What is the temperature? So temperature is unknown. We do know that it needs to be in Kelvin, though. Oh man, we don't know R. Looks like we can't solve this problem ever. Psych. R is the ideal gas constant. Just like Planck's constant, or the speed of light, it is constant. It is always the same. It never changes. So anytime you see R, you're always going to put in 0.0821. Every time. There's no exceptions. Anytime you see R, you put the ideal gas constant, 0.0821. Okay, now let's rewrite our formula and fill in what we know. PV equals nRT. Pressure was 5.6 times volume, which is 12, equals moles, which is 4, times ideal gas constant, 0.0821, times temperature, which was unknown. From here, it's just a calculator problem. 5.6 times 12 gives us 67.2. And then our ideal gas constant times 4, 0.3284 times x, our unknown. Let's divide both sides by ideal gas constant. So 67.2 divided by 0.3284, 204.62850, etc. Just like always. 1 decimal place. So it's going to be 204. Here's the 6. Look at the 2 for rounding. Stays the same. 204.6. Oh wait, this is a temperature. Kelvin. So there's a little bit more to these kind of problems, but they're still pretty easy. Just like any other problem that I give you, there's only one variable that you don't know. So you just have to solve it. Okay, next. This is supposed to be a degree sign, not a 0. So that's my bad. If I have an unknown quantity of a gas at a pressure of 1.2 atmospheres, a volume of 31 liters, and a temperature of 87 degrees Celsius, how many moles of gas do I have? So the question wants to know how many moles, which means we're looking for N. So when we rewrite our variables, we have P, V, N, R, T. We already know that N should be our unknown. We know that the ideal gas constant is 0.0821. I gave you a pressure of 1.2 atmospheres, 1.2 atmospheres, a volume of 31 liters, and a temperature of 87 degrees Celsius. Whoops, we don't use Celsius, we use Kelvin. So you take Celsius and add 273 to get Kelvin. So 87 plus 273 gives us 360 Kelvin. Not going to use that. We use 360 Kelvin. Cool. We only have one unknown. We can easily solve these. So PV equals nRT. P comes from right here, is 1.2 times V, which is right here, 31, equals N, which is unknown, times ideal gas constant, R, 0.0821, times T, temperature, which is right there. Don't be a goof and use Celsius. Always use Kelvin. Now, we just multiply. 1.2 times 31 is 37.2. And then we get 360 times ideal gas constant gives us 29.556x. Now we're going to divide both sides by 29.556. And that gives us 1.3. That's a number. We don't like naked numbers. We need a unit. Our unit for moles is moles. 1.3 moles. Done. Nice. Okay. So number 3, if I have 3 moles of a gas in a container with a volume of 60 liters and a temperature of 400 Kelvin, what is the pressure inside the container? I want you guys to solve this one. When you have the answer to number 3 for ideal gas law, take that answer and the answer to number 4 from Dalton's law of partial pressure. You're going to go to Google Classroom and you're going to post what you think those answers are in the form that's there. So here's number 3 again. Make sure to pause the video, get your answer. All right.